question is, given the steady incompressible velocity distribution v is equal to 3x I plus cy j plus 0 k, where c is a constant. If the conservation of mass is satisfied, the value of c should be, which of the options will be the answer for c? So, the velocity distribution is given as v is equal to 3x I plus cy j plus 0 k. So, and it is given that the flow is steady and incompressible flow. So, for an incompressible flow, the mass conservation equation becomes the divergence of velocity is equal to 0. So, in the velocity profile is given in Cartesian coordinates. So, if we substitute for the divergence, we will get I dou by dou x of plus j dou by dou y plus k dou by dou z of three x I plus cy j plus 0 k equal to 0. So, this will be dou by dou x of 3x plus dou by dou y of cy plus dou by dou z of 0. So, which will be 0 equal to 0. So, this will be 3 plus c equal to 0, which gives c equal to minus 3. The next question is, given the steady incompressible velocity distribution v is equal to 3x I plus cy j plus 0 k, so the same velocity profile where c is a constant, the shear stress tau xy at the point xyz is given by. So, the velocity profile is again v is equal to 3x I plus cy j plus 0 k. So, the xy component of stress tensor is asked, which is tau xy is equal to mu into dou u by dou y plus dou v by dou x. Here u is the velocity component in the x direction and v is the velocity component in the y direction. So, if we substitute our velocity components to this particular equation, we will get mu into dou by dou y of 3x plus dou by dou x of cy. It is given that c is a constant and this term does not contain any y and this term does not contain any x. So, tau xy will be mu into 0. So, tau xy will be 0. The next question is, if for a laminar flow in a smooth straight tube, the tube diameter and length both double while everything else remains the same, the volume flow rate will increase by a factor of, so out of which by which factor the volumetric flow rate will increase. So we know the laminar flow in a circular tube can be defined by, or can be defined by the Hagen-Poiseuille equation. So which is delta P by L is equal to 32 V bar mu by d square. So here delta P is the pressure drop, L is the length of the tube, V bar is the average velocity, mu is the viscosity, and d is the diameter of the pipe. So it is given that the tube diameter and length are doubled, everything else is kept constant. So we will first write V in terms of the flow rate. So V is equal to Q divided by area. Q is the volumetric flow rate by d square by 4. So if we substitute, delta P is equal to L into 32 Q by pi d square by 4 into mu divided by d square. So delta P is proportional to L into Q into delta P is proportional Q divided by d raised to 4. So in the first case, in the second case, the L is doubled and d is also doubled. So and the delta P remains constant. So the delta P for the second case L dash into Q dash divided by d dash raised to 4. So d dash is 2d and L dash is 2L. So delta P dash is equal to 2L Q dash divided by 2 raised to 4 into d raised to 4. And we know that delta P is equal to delta P dash. So L into delta P is equal to delta P dash, which means that L into Q by d raised to 4 is equal to 2L Q dash divided by 2 raised to 4 into d raised to 4. So from this you can get Q dash as, this L is gone, d raised to 4 and d raised to 4 is gone. So this cube, Q dash is equal to 2 cube into Q, so which is 8Q. So the answer is 8 times. The question is, an idealized velocity field is given by the formula V is equal to 4txi minus 2t square yj plus 4xzk. Is this flow field steady or unsteady? Is it 2 or 3 dimensional? At the point xyz is equal to minus 1, 1, 0, compute the acceleration vector and any unit vector normal to the acceleration. So, the velocity vector is given. V is equal to 4txi minus 2t square yj plus 4xzk. So, is this flow steady or unsteady? So, as you can see, there is a term, each term contains, so not each term, the x component velocity and y component velocity contains t, which means that with respect to time the velocity changes, which means that the flow is unsteady. And is it 2 or 3 dimensional? So, the velocity is dependent on all the coordinate axes, all the coordinate variables, that is x and y, x, y and z. So, since it depends on each variable, the flow is 3 dimensional. So, flow is unsteady and 3 dimensional, and we are asked to calculate the velocity, we are asked to calculate the acceleration vector. So, if you see the left hand side of Navier-Stokes equation, which gives you the acceleration. So, acceleration is basically dou, so V by dou t plus V dot del V. This is the acceleration vector. So, if we write this in each component, in the x component, this equation becomes dou u by dou t plus v dot del u. So, here this is vector and this is the x component, this is the ax. So, if we substitute to this formula, we get ax equal to dou u by dou t, dou by dou t of u is 4tx plus v. V is our velocity vector, 4txi minus 2t square yj plus 4xzk dot del u. Del u will be, this is dotted with I dou by dou x of u is 4tx dou by dou y of 4tx plus k dou by dou z of 4tx. So which you will get 4x plus, so each component will be multiplied, 4tx into dou by dou 4t. 4tx into 4t will be 16 t square x, and minus 2t square into dou by dou y of 4tx. So this becomes 0, and this one dou by dou z of 4tx, this will also be 0. So the acceleration, x component of acceleration will be 4x plus 16x t square. Similarly, for the y component of acceleration, ay will be dou v by dou t plus v dot del v. So this v is the velocity vector and this v is the y component of velocity, and this v is also the y component velocity. So if we substitute dou by dou t of v is minus 2t square y plus 4txi minus 2t square yj plus 4xzk dotted with I dou by dou x of minus 2t square y plus j dou by dou y of minus 2t square y plus k dou by dou y of minus 2t square y. So this becomes minus 4ty plus, so this term becomes 0 because it does not contain any x, and this term becomes minus 4ty, sorry, this term becomes minus 2t square, and this term, sorry, this is dou by dou z, so this term becomes 0. So your equation will be your form. Minus 2t square y into minus 2t square y into minus 2t square. Which is equal to minus 4ty plus 4t raised to 4y. For the acceleration in z direction, your az is equal to dou w by dou t plus v dot del w. Substituting, we will get dou by dou t of 4xz plus four txi minus 2t square y j plus 4xz k dotted with I dou by dou x of 4xz plus j dou by dou y of 4xz plus k dou by dou z of 4xz. So you will get, so this doesn't contain any time, so that will be 0 plus 4tx into, and this derivative becomes 4z, and this becomes 0, this becomes 4x. So this multiplied by this will give 0, and this multiplied by this gives 16 x square z. So 4tx 16 x z t plus 16 x square z. This is your acceleration in the z direction. And so writing it together, you will get a is equal to 4x plus 16 t square x into I plus minus 4ty plus 4t raised to 4y t raised to 4y into j plus 16 xz t plus 16 x square z into k. This is your acceleration vector. And yeah, at minus 1 1 0, this has the value a is equal to if you substitute, you will get, so at minus 1 1 0, you will get minus 4 plus 16t square, right? So you can, so you will get the following: minus 4 into 1 plus 4 t square I. So what you do is you substitute minus 1 1 0 for x, y and z. So you will get the following: minus 4t t 1 minus t cube j plus 0 k. So, if you can see, there is no z component at this particular point. So, which means that the acceleration is in the xy plane. So next we need to find out any unit vector normal to this acceleration. So, since this is lying in the xy plane, z axis can be considered as the normal vector, which means that k can be taken as normal vector. Vector to this acceleration at this particular point. Yeah, thank you. I have one more, I think. So, the next question is, a frictionless incompressible steady flow field is given by V is equal to 2xyi minus y square j in arbitrary units. Let the density be rho 0 equal to constant and neglect gravity. Find an expression for the pressure gradient in the x direction. So, what we do is, we are given the velocity field 2xy I minus y square j. We need to find out the pressure gradient. So, we just have to substitute this velocity into the Navier-Stokes equations. So, Navier-Stokes is rho into dou v by dou t plus v dot del v is equal to minus grad p plus mu del square v. This is in the vector form. So, we write in each component, each component. So, rho is equal to, in the x component, rho into dou u by dou t plus v dot del u is equal to minus dou p by dou x plus mu del square u. So, substituting to this, we will get rho into, rho is given, which is rho 0. It is a steady flow, there is no time dependence. So, this term becomes 0. So, you have this term 2xy into I minus y square into j into dot del u. Del u is I dou by dou x of u is 2xy plus j dou by dou y of 2xy plus k dou by dou z of 2xy, which is equal to minus dou p by dou x plus mu into del square u, dou square by dou x square of u is 2xy plus dou square by dou y square of 2xy plus dou square by dou z square of 2xy. So this part becomes rho 0 into 2xy into, so this is 2y, 2xy into 2y, and this minus y square into 2x, dou by dou y of 2 xy is 2x, y square into 2x is equal to, and there is no z component, so it is 0. So equal to minus dou p by dou x plus mu into, so this derivative is dou by dou x, dou square by dou x square of 2xy, which is 0, and this is also 0, all the terms are 0. So you get dou p by dou x is equal to rho 0 into minus rho 0 into 4xy square dou p by dou x is equal to minus rho 0 into 4xy square minus 2xy square is equal to minus rho 0 into 2xy square. Similarly, in the y direction, you will get dou v by dou t plus v dot del v is equal to minus dou p by dou y plus mu del square v. Substituting, we get after substituting everything, you will get dou p by dou y is equal to minus rho 0 into 2y cube. You can do the same, you can follow the same way I did for dou p by dou x. So finally the z component will be 0 because there is no z direction velocity, and so if you substitute all the components to the z direction, z component, you will get 0. So finally del p, the velocity gradient, pressure gradient is minus rho 0 2x square 2x y square I plus 2y cube j. This will be the pressure gradient. Thank you.